So activation functions. So what are activation functions? Let's see. Let's say we have this neuron. We have picked some random neuron from any layer, let's say. So these are the inputs coming towards neuron x1, x2, x3, and these are the weights w1, w2, w3. Now what happens here at this neuron or in this neuron, right? In this neuron here, we we take the sum of products of weights and inputs. So what I'm saying is, what we do is we have x1, w1, this input gets multiplied with this weight, plus this input gets multiplied with this weight, plus this input gets multiplied with this weight x3, w3, right? So this sum takes place here, right? So if I write this as sum symbol, or if I write this sum as sum over I is equal to 1 to n, if we have n inputs, so xi, wi, this is what happens here, right? Now what we do here, now after this sum, here we have what is called as a function. We apply this function on this sum, right? We have a function here, right? We write it as f, right? So we apply this function f on this sum, and xi, wi. Now if I call this sum, let me call this sum as z. So z, right? So if I write f of z, I'm writing z for this sum, like f of z. Now applying this function on this sum or this z gives us the output of this neuron, O, right? So this function, right? So O is equal to f of z. So this function f, which is there in this neuron, is called as activation function. Activation function. So what are the different activation functions available? So there are quite a few activation functions available which are widely used. So the first activation function which is widely being used today is called as ReLU. ReLU. So ReLU stands for rectified linear unit. Right? So that is ReLU is being used from I think from 2012 when deep learning became very much popular, and ReLU is one of the reason why deep learning became very popular. So pre-deep learning, that means pre 2012 or pre in late in 90s and 80s and early 2000, there were two activation functions which were widely used. The first one is called as or if I write A, it's called as sigmoid activation function, and the second one or B is called as tanh. So these were the two activation functions which were popularly used before the advent of ReLU. So let us see these functions one by one. So sigmoid activation function, sigmoid is denoted like this. It is denoted by sigma of z. So we are applying this function, right? This function I'm talking about. This function is it can be ReLU, it can be sigmoid, it can be tanh. These are the three popular activation functions. So now ReLU is most popular. So but before ReLU, as I said, sigmoid and tanh were the most popular activation functions. So this f I'm talking about. So if I say this f as sigmoid, so this will become sigmoid of z. Sigma, right? We write like this: sigma of z, right? So sigma of z is equal to, the formula of sigmoid is e power z divided by 1 plus e power z, which is equal to 1 upon 1 plus e power minus z. If I simplify this, I get this. Right? And this activation function is also, used in logistic regression, right? It's one of the most important part of logistic regression. So now there are many reasons why the sigmoid was being used as an activation function, but one of the most important reason is, if I take the derivative of sigmoid, of z with respect to z, the derivative of sigmoid of z looks like this. It is sigma of z into 1 minus sigma of z. So this is the derivative of course we are not deriving, we are not writing the derivation here, but I directly wrote the derivation. Derivative of sigma. So derivative of sigma, if you observe, is in terms of sigma only on the right hand side of this equation. If you see, I have sigma here and sigma here. There is no other term, right? So what is the advantage of this? You see, in the neural network, in the forward propagation, in every neuron, if we have a sigmoid activation function, we are already computing the sigmoid of z. In every neuron, we are already computing this sigma of z in the forward propagation phase. And while using back propagation algorithm, we have two phases. The first one is forward propagation, in which we pass the input in the forward direction, and that time we apply the activation function in each neuron. That means we compute, if the activation function is sigmoid, we compute sigma of z. Now in the back propagation phase, what we do, we need to compute the derivatives. We need to compute a lot of derivatives of activation function, right? If you remember, we were saying dou w of, or dou L, not dou w, derivative of loss with respect to w is equal to derivative of loss with respect to some output, right? Some output OI, and then derivative of OI with respect to derivative of loss. So this OI is nothing but the derivative of activation function, because this output is coming out from the activation function. If I this OI is nothing but sigma f of, or sigma of some here, right? This sigma, this is sigma, right? So this OI is nothing but coming out of this sigma, right? So ultimately we'll be deriving this sigma, taking the derivative of this sigma. That means in the backward propagation phase, we will need to compute the derivative of sigma. And you see, what is the formula of derivative of sigma? This is the formula, and in the formula I have only sigma, which I already computed. That means in the back propagation phase I need not do any work. I have already computed these sigmas, right? I just need to plug in the values which I already computed, right? So that is one of the important point about this sigmoid activation function. The derivative of sigma is in terms of sigma itself, right? Okay, now if we see the graph, if I show you graph of sigma quickly, the graph of sigma looks like this. Let's say, so if I plot it, if this is 0.2, 0.4, 0.6, 0.8, and 1.0, and if this is, let me plot the graph. The graph literally looks like this. So at 1, the maximum value of sigma is 1, right? And it is a S-shaped curve. This is sigma. Sorry. So it is S-shaped curve. The minimum value is 0 and the maximum value is 1, right? So the sigmoid function is a tapering function. That means it tapers off after 1, right? The value of sigma does not go beyond 1. The maximum value of sigma is 1. The value of sigma varies between 0 and 1. The value of sigma, this is the graph S-shaped curve is for sigma. So if I if I write, so 0 is less than equal to sigma of z, and which is less than equal to 1. So the maximum value of sigma is 1, minimum value is 0. So that's the important point. Now if I plot the derivative of sigma, it will look like this. So this is approximate curve for derivative of sigma. This is derivative of sigma, right? Now if I this say this is minus 4 and this is plus 4, for example. Now if I talk about this derivative, it's the shape of this is a bell-shaped curve, right? Bell-shaped curve, and the important point is derivative of sigma is uh, in between 0 and 1, right? So if I write 0 is less than equal to the derivative of sigma with respect to z, and which is less than equal to, not less than equal to, but it's strictly less than 1. The derivative of sigma is strictly less than 1. So the derivative of sigma varies between 0 and 1. So this derivative of sigma is strictly less than 1. The important takeaway from this is the derivative of sigma is less than 1. It's between 0 and 1, and strictly less than 1. So this is the important takeaway. So derivative of sigma. That's why I have drawn this curve. So because will need this knowledge when we'll understand a very important problem with this activation function sigmoid and ReLU. That problem is called as vanishing gradient problem. So for that time we'll need this knowledge. The derivative of sigma varies between or is less than 1. It's like 0.3, 0.2, 0.05, like this. The derivative of sigma is like this, right? Okay, so that was sigmoid activation function. Another activation function is called as tan h. Tan h. So tan h is equal to, if I write tan h is equal to e power z minus e power minus z divided by tan h of z, of course, e power z plus e power minus z. So this is tan h activation function, formula for tan h activation function. And if I take the derivative of tan h with respect to z, it is 1 minus tan h square of z. So again, the important point about tan h is the derivative of tan h is in terms of tan h, right? You see on the RHS you have tan h, right? It's very similar to sigma. The derivative of sigma, a sigmoid function, was in terms of sigmoid itself. So the same case for tan h. That means once you compute tan h in the forward propagation, you need not do any work while you are doing back propagation, or while you are doing updation in the weights. And that time you will compute the derivatives. You need not do any work because derivatives in terms of tan h. Okay, so again, if I plot the graph for tan h, just I'll show you quickly. If this is minus 1 here and this is plus 1, so minus 1 here, this is minus 1. So the derivative of tan h is, this tan h looks like this, right? So this is minus 1 and plus 1. This is 0, right? And this curve is a tan h curve. Tan h, right? Now the important point to note is tan h varies between minus 1 less than equal to tan h, which is less than equal to plus 1. So in case of sigma was varying between 0 and plus 1. So tan h varies between minus 1 and plus 1. But the curves are exactly same. The shape of the curve is exactly same. This is also a S-shaped curve, right? So, and now if I plot the graph for the derivative of tan h, it will look like this. So this is how the graph for derivative of tan h. This is derivative of tan h with respect to z. This is tan h of z. Okay. And this, of course, this is z here. So here also I forgot. So this is z. So if we look at the shape of this derivative curve, this is also similar to the shape of a sigmoid curve, right? Of course, this is slightly bigger curve than sigmoid. So now if I write the function, if I write the how this derivative is behaving, it is in between it is 0 is less than equal to derivative of tan h, which is less than equal to 1. So derivative of tan h is varying between 0 and 1. So it can be equal to 1 also. In case of sigmoid, the derivative of sigmoid was right, sigma of z with respect to z. It was less than 1, strictly less than 1, but the derivative of tan h is, it can be equal to 1 also, right? But the shape of this derivative of sigmoid, and now if I plot here, if I plot sigmoid on the same graph, the derivative of sigmoid will look like this. This is the derivative of sigmoid, and if I plot sigmoid itself will look like this, right? So this is, these red curves are for sigmoid, but the point to observe is the shapes of these curves are very similar, right? Again, the point to note is the derivative is derivative of sigma tan h is also like 0.4, 0.3, 0.5, 0.05, etc. Right? So, these were the two important activation functions pre deep learning era, pre ReLU, or before the advent of ReLU. So we understood the shapes of sigmoid, derivative of sigmoid, tan h, and derivative of tan h. So the important takeaway from this is the derivatives are less than, greater than 0 and less than 1 for sigmoid, and for tan h the derivative is greater than 0, greater than equal to 0, and less than equal to 1, right? So derivative of sigmoid is greater than equal to 0 but less than, strictly less than 1, and for tan h greater than equal to 0 and less than equal to 1. Okay, these are the two important takeaways, and we'll use this knowledge in the next video to understand what is the problem if these are the derivatives, right? Okay.